Day 13 of 60 in our DSA in Rust challenge. And today HashSet teaches you something Python and Java quietly hide. Here's the interview question. Given a list of integers, find every duplicate in O in time. You could sort and scan, but that's O in log n, and worse, it skips the real lesson. Rust's HashSet won't just make this fast. It'll force you to think about what the same value even means. Stick around, because the borrow checker is about to teach you a pattern you'll use in every algorithm from here on. Start with the type itself. HashSet T carries a bound. T must implement EQ plus hash. For built-in types like i32 or string, those traits already exist, so HashSet new just works. But the moment you store a custom type, say a struct point x, i32, y, i32, the compiler stops you. It needs to know how to hash your value and how to compare two of them. The fix is one line. Hashtag, derive, partial EQ, hash, above your struct. That derive is a contract. You're telling the compiler 2 points are identical when both fields match. This is the part that matters. In Python, a set compares by whatever underscore and hash happen to do, and surprises hide until runtime. In Rust, identity is explicit and checked at compile time. When you derive hash and EQ, you're declaring the rule for equality up front in the type system. There's no mystery later about why two objects collided or didn't. That explicitness feels like extra work on day 13, but it's exactly why a Rust hash set is safer to reason about. The equality contract lives in the code, not in your memory. Now the duplicate finder. You iterate the slice, and for each number you want to know, have I seen this before? The naive instinct is to write if set.contains n, dups push n, else set.insert n. That works, but it touches the set twice and reads awkwardly. Here's the idiomatic move. Insert returns a bool. True means the value was newly added. False means it was already present. So if set.insert n, dups push n, does both jobs in one call. One lookup, one decision, newly inserted, or a duplicate. That return value is doing real work. But try mixing borrows and you'll meet the borrow checker. Say you grab a reference into the set, let first equals set.iter.next, and then call set.insert n, while first is still alive. The compiler rejects it. You can't hold an immutable borrow of the set and mutate it at the same time. Contains takes T, it borrows. Insert takes T, it owns. That's the footgun. The fix is to not hold a reference across the mutation. Finish your read, drop the borrow, then insert. Structure your logic so the query and the mutation don't overlap, which, conveniently, the insert returns bool pattern already does for you. Watch the ownership detail with non-copy types. For i32, which is copy, set.contains n is painless. N is still yours afterward. But with a string, contains wants string, and insert consumes the string by value. So you check membership with a borrow, set.contains path, then move the value in with set.insert path. Order matters. Query first while you still own the borrowable value, then hand over ownership. Get that backwards, and you're cloning just to satisfy the compiler, a tax you don't need to pay. Same hash set, harder problem, longest consecutive sequence. Dump every number into a HashSet32. Then for each n, ask, is n 1 in the set? If it isn't, n is the start of a run. Walk forward, n plus 1, n plus 2, calling contains until the chain breaks, counting the length. Because each number is only the start of one sequence, this is O, n, total. No sorting, no index math, just ownership-safe membership queries. That's the payoff. The same contains you fought the borrow checker over now powers an elegant linear algorithm. Day 13 done. The takeaway. HashSet in Rust isn't just a fast membership check. It's a contract about identity, enforced at compile time, and the insert returns bool pattern dissolves the borrow conflict before it starts. Query with a borrow, mutate by value, never hold both at once. Subscribe for day 14.